So here's something to think about as you're lying there, getting comfortable, letting the day wind down. You live in a world of 3 dimensions. You move forward and back. You move left and right. You move up and down. That's it. That's all the directions you've got. And for most of human history, nobody really questioned that. 3 directions of motion, 3 axes, 3 coordinates to pin down where anything is in space. It seems so obvious it's barely worth mentioning, like pointing out that water is wet. But here's the thing. Some of the deepest, strangest, most beautiful ideas in all of mathematics and physics come from asking a question that sounds almost childish. What if there were more? What if 3 dimensions aren't the whole story? What if space itself has directions we can't see, can't point to, can't even properly imagine, but that are, in some very real sense, there? And the wild part is, this isn't just abstract speculation. Higher dimensions aren't just a game mathematicians play for fun, though they do have fun with it. The idea of extra dimensions sits at the heart of how we understand gravity, how we describe the shape of the universe, how string theory tries to unify all of physics, and even how machine learning algorithms process your voice when you talk to your phone. Dimensions, it turns out, are everywhere. We just need to learn how to think about them. But let's not rush. Let's take this slow, because this is one of those topics that actually gets clearer the more gently you approach it. And honestly, the history of how people came to understand dimensions, who figured out what and when and why it was so controversial. That story is genuinely fascinating. So let's start at the very beginning, and I mean the real beginning, with the ancient Greeks, because that's where the formal idea of dimension first shows up in anything like a rigorous way. Euclid, around 300 BC in Alexandria, wrote a book called The Elements. You've probably heard of it. It's one of the most influential texts ever written. For about 2,000 years, it was basically the textbook for all of mathematics. And right there in the Elements, Euclid lays out what a point is, what a line is, what a surface is, and what a solid is. He doesn't use the word dimension the way we do, but the hierarchy is crystal clear. A point has no parts. It's just a location, nothing more. A line has length, but no breadth. A surface has length and breadth, but no depth. And a solid has all 3, length, breadth, and depth. 0, 1, 2, 3. That's the ladder, and for Euclid, the ladder stops at 3. There's nothing above a solid, 3 dimensions of space, and that's the end of it. And you know what? For a very, very long time, nobody argued with that. Why would they? You can look around the room you're in and confirm it. Everything you can touch, everything you can build, every object that exists, occupies 3-dimensional space. Euclid's framework wasn't just mathematically elegant, it matched reality perfectly. So the idea that dimension could go higher than 3 wasn't just unfamiliar, it was almost unthinkable. It would be like suggesting there's a direction you've never noticed, a way of moving that no one has ever moved. It sounds like nonsense, but let's sit with Euclid's hierarchy for a moment, because there's something really beautiful hiding in it, something that becomes a key insight later. Think about how you go from one level to the next. You start with a point, 0 dimensions, no size at all. Now take that point and drag it in a direction. Sweep it along, and it traces out a line. You've gone from 0 dimensions to 1. Now take that line and drag it in a new direction, a direction perpendicular to the line itself, and it sweeps out a flat surface, a rectangle, say. You've gone from 1 dimension to 2. Now take that surface and drag it in yet another new direction, perpendicular to both of the directions you've already used, and it sweeps out a solid, a box. 2 dimensions to 3. Makes sense, right? Each time, you take the thing you've already got and you extend it in a brand new direction that's at right angles to everything before. And here's the question that will keep coming back throughout everything we talk about tonight. What happens if you do it one more time? What if you take that box, that 3-dimensional solid, and you drag it in a new direction, a 4th direction, one that's perpendicular to all 3 directions you've already used? You can't picture it. I can't picture it either. Nobody can. Not really, because our brains evolved to navigate 3-dimensional space, and that's all the spatial imagination we were given. But mathematically, there's absolutely nothing stopping you. The operation is identical every single time. You take the thing, you extend it in a new perpendicular direction, and you get the next thing up. The math doesn't care whether you can visualize it. The math just works. But we're getting ahead of ourselves. That realization that the math works even when the visualization fails took a surprisingly long time to arrive. Let's stay in the ancient world for another moment, because there's a figure who almost got there, and his story is worth knowing. Aristotle, who came just a generation before Euclid, actually wrote about dimensions quite explicitly. In his work on the heavens, he argues that 3 is a special number, that the physical world is complete in 3 dimensions, that there is no magnitude beyond length, breadth, and depth, and therefore no body or spatial extension beyond the solid. He even uses a kind of mystical argument, connecting 3 to the ideas of beginning, middle, and end, suggesting that 3 is the number of completeness. And Aristotle's authority was enormous. For nearly 2 millennia in the Western intellectual tradition, if Aristotle said 3 dimensions was all there was, then 3 dimensions was all there was. The case was closed. Now there were hints and glimmers along the way. In the 2nd century, Ptolemy, the great astronomer, also working in Alexandria, actually tried to give a proof that a 4th spatial dimension was impossible. His argument was essentially geometric. You can draw 3 mutually perpendicular lines through a point, he said, but you cannot draw a 4th. Therefore, 4 dimensions cannot exist. It's a fascinating moment in intellectual history, because Ptolemy is confusing a limitation of physical space with a limitation of mathematics itself. He's saying, I can't build it with sticks, so it can't exist. And in a way, you can't blame him. The tools for thinking about dimensions abstractly simply didn't exist yet. So for a very long time, we're talking centuries and centuries, the number 3 was treated almost as a law of nature and a law of mathematics simultaneously. No distinction made between the two. Geometry was the study of the space we live in, and the space we live in has 3 dimensions, so geometry has 3 dimensions. End of discussion. The first real cracks in that wall didn't appear until the 17th century, and they came from an unexpected direction: algebra. See, here's what happened. In 1637, René Descartes published an appendix to his discourse on method called La Géométrie, and in it, he did something revolutionary. He showed that you could describe geometric shapes using equations. A circle isn't just a round thing you draw with a compass. It's the set of all points satisfying x squared plus y squared equals r squared. A line isn't just a mark on paper. It's an equation like y equals mx plus b. Descartes married algebra and geometry, and the offspring was what we now call analytic geometry, or coordinate geometry. And this is where things get quietly profound. Because once you're describing geometry with coordinates, with x and y and z, there's a very natural question that starts whispering at the edge of your mind. You've got X. You've got Y. You've got Z. What's stopping you from writing down a W? What's stopping you from writing an equation with 4 variables instead of 3? Algebraically, nothing. You can write x squared plus y squared plus z squared plus w squared equals 1. And that equation is perfectly well defined. It describes something. You just can't draw it. Descartes himself didn't go there, not explicitly. But he planted the seed. By turning geometry into algebra, he inadvertently opened a door that would eventually lead straight into higher dimensions. Because algebra doesn't care about your ability to visualize. Algebra is just symbols and rules and relationships, and those symbols can have as many variables as you want. It took a while for anyone to walk through that door, though. The 17th and 18th centuries were busy with calculus. Newton and Leibniz, and all the incredible machinery that came from their work. And most mathematicians were focused on problems in 2 and 3 dimensions, because those were the problems that physics kept handing them. Orbits of planets, trajectories of cannonballs, the shapes of vibrating strings, all very 3-dimensional stuff. But there were scattered moments, little hints, where the idea of higher dimensions peeked through. In 1754, Jean-Laurent d'Alembert, a French mathematician and philosopher, one of the editors of the famous Encyclopédie, wrote an article in which he suggested that time could be thought of as a 4th dimension. He was being somewhat metaphorical, but the idea is striking. He pointed out that if you need 3 numbers to specify where something is in space, you need a 4th number to specify when it is. So the complete description of an event, not just a location, but a moment, requires 4 coordinates, 3 of space, 1 of time. And if a dimension is just an independent number you need to pin something down, then time is a dimension. Now, d'Alembert was careful about this. He presented it almost as a thought experiment, a philosophical curiosity. But the idea was out there, and it's an important one, because it starts to decouple the concept of a dimension from the concept of a spatial direction. A dimension doesn't have to be a direction you can point in. It can be any independent quantity. Temperature could be a dimension. Color could be a dimension. Price could be a dimension. Anything that varies independently, anything that requires its own number to describe, can be thought of as a dimension. And once you see it that way, the universe of dimensions explodes wide open. But let's not get too abstract too fast. Let's come back to the people, because the real revolution in higher dimensional thinking, the moment when mathematicians stopped being coy about it and started seriously, rigorously working with spaces of 4, 5, 10, 100 dimensions, that moment has some very specific names and dates attached to it, and it happens in the 19th century, which is honestly one of the most extraordinary centuries in the entire history of mathematics. The person who arguably deserves the most credit for making higher dimensions, mathematically respectable, is a young German mathematician named August Ferdinand Mobius. Yes, the same Mobius of the Mobius strip. That wonderful one-sided surface you can make by taking a strip of paper, giving it a half twist, and taping the ends together. Mobius was a geometer, a deep thinker about shape and space, and in 1827 he published a book called The Barycentric Calculus, in which he made an observation that sounds simple, but is actually quite deep. He pointed out that certain geometric operations that are impossible in 3 dimensions become possible if you allow a 4th dimension. Specifically, he noted that a 3-dimensional object that is a mirror image of another, like your left hand and your right hand, cannot be rotated into its mirror image within 3-dimensional space. No matter how you twist and turn your left hand, you cannot make it into a right hand, But if you could pick it up and flip it through a fourth spatial dimension, you could. Just as you can flip a letter R on a piece of paper into its mirror image by lifting it off the paper and turning it over in three-dimensional space, you could flip a left hand into a right hand by rotating it through four-dimensional space. Mobius didn't develop this into a full theory of four-dimensional geometry. He mentioned it almost in passing, but the insight is electric because it shows that a fourth dimension isn't just an algebraic abstraction. It would have real geometric consequences. It would let you do things that are otherwise impossible. And that idea, the idea that higher dimensions have tangible geometric meaning, was about to be picked up and run with by one of the most brilliant and tragically short-lived mathematicians who ever lived. A young man who would give a single lecture in 1854 that would reshape our understanding of space itself, a lecture that even Einstein, half a century later, would call one of the great intellectual achievements of the 19th century. His name was Bernhard Riemann, and when he stood up to deliver that lecture on the 10th of June, 1854, he was 37 years old, nervous, and relatively unknown outside a small circle of German academics. He would be dead within 12 years from tuberculosis at the age of 39. But in that single afternoon, in a modest lecture hall at the University of Göttingen, he laid out a vision of space and geometry so radical, so far ahead of its time, that the full implications wouldn't be absorbed for decades. Let me set the scene for you, because it's worth savoring. In German universities at that time, there was a tradition called the Habilitationsschrift. It was essentially a qualifying lecture that a young scholar had to deliver before being allowed to teach at the university level. The candidate would propose several possible topics, and their doctoral advisor would choose one. Riemann's advisor was Carl Friedrich Gauss, who was by then in his 70s and widely considered the greatest mathematician alive, possibly the greatest who had ever lived. Riemann submitted 3 possible topics. 2 of them were on subjects he'd already worked out thoroughly. The third, which he probably included as a formality, was on the foundations of geometry. Gauss, to Riemann's alarm, chose the third one, the one he hadn't fully worked out yet. Now, imagine being in Riemann's position. You're a shy, deeply introverted young man. You've struggled with anxiety your entire life, and the most famous mathematician in the world has just told you to stand up and explain, from scratch, what geometry really is, and you have to do it in a way that impresses him. The pressure must have been extraordinary. Riemann reportedly worked himself into a state of near collapse preparing for it, and at several points considered abandoning the whole effort. But he didn't. He pushed through, and what he produced was a lecture titled "On the Hypotheses Which Lie at the Foundations of Geometry." It's one of the most important scientific documents ever written, and it's remarkably short, only about 15 pages in printed form. You could read it in an hour, but the ideas in it would take the world half a century to fully digest. Here's what Riemann did, and I want to explain this gently, because it's one of those ideas that sounds complicated at first, but is actually deeply intuitive once you let it settle in. He asked a question that nobody had really asked before, at least not with this kind of precision. He asked, "What is a space?" Not what is this space, the space we live in, but what is space in general? What are all the possible kinds of space that could exist, and how do you describe them mathematically? Think about what that question implies. Before Riemann, geometry was essentially the study of the space we happen to inhabit. Euclid's geometry described flat space, the kind of space where parallel lines never meet, where the angles of a triangle always add up to 180 degrees, where the shortest distance between 2 points is a straight line. And for over 2,000 years, people assumed that was the only kind of geometry there was. It wasn't just a description of space. It was space, period. Kant had even argued that Euclidean geometry was a necessary truth of human cognition, that we couldn't even conceive of space being any other way. But by Riemann's time, cracks had appeared. In the early 1800s, mathematicians like Nikolai Lobachevsky in Russia and János Bolyai in Hungary had independently discovered that you could construct perfectly consistent geometries where Euclid's parallel postulate didn't hold. Where, for instance, through a point, not on a given line, you could draw infinitely many lines that never intersected the original. These were called non-Euclidean geometries, and their discovery was shocking. It meant that Euclidean geometry was not the only logically possible geometry. It was one option among several. But Lobachevsky and Bolyai had only found specific alternatives. What Riemann did was something far more sweeping. He created a general framework, a way of describing any possible geometry in any number of dimensions, with any kind of curvature. He didn't just find another geometry. He built the machine for generating all geometries. And here's the key insight, the one that makes everything click. Riemann said that a space, any space, is defined by the way you measure distances in it. That's it. If you can tell me how to calculate the distance between any two nearby points, I can tell you everything about the geometry of that space. Whether it's flat or curved, whether it has 2 dimensions or 3 or 7 or 100, all of that information is encoded in the distance formula. Let me give you an analogy. Think about the surface of the Earth. If you're an ant crawling on a flat table, measuring distances is simple. You just use a ruler, and the Pythagorean theorem works perfectly. The square of the distance equals the square of the east-west separation plus the square of the north-south separation. Nice and clean. But now, put that ant on the surface of a sphere, like the Earth. Suddenly, the Pythagorean theorem doesn't quite work anymore. If you try to measure the distance between 2 cities using a flat map, you'll get the wrong answer, because the surface is curved. The actual shortest path between 2 points on a sphere isn't a straight line. It's an arc, a segment of a great circle. And the formula for distance on a curved surface is more complicated than the flat space version. It has extra terms that account for the curvature. What Riemann realized is that you can encode all of the geometric properties of any space, its curvature, its shape, its dimensionality, into a mathematical object that describes how distances work at every point. This object is now called the metric tensor, and it's basically a little grid of numbers at every point in space that tells you how to convert coordinate differences into actual distances. In flat space, the metric tensor is simple and constant. On a curved surface, it varies from point to point. And here's the beautiful part. This framework works in any number of dimensions. You can write down a metric tensor for a 2-dimensional surface, or a 3-dimensional space, or a 4-dimensional space, or a space with any number of dimensions you like. The mathematics doesn't care. It just works. And this is where it gets really interesting for our purposes, because Riemann explicitly discussed the possibility that the space we live in might not be flat. He suggested, and remember, this is 1854, 60 years before Einstein, that the geometry of physical space might be curved, and that the curvature might even be related to physical forces. He didn't develop this idea in detail, because he didn't have the physics to back it up. But he planted the seed. He said, essentially, the shape of space is not something you can determine by pure thought alone. It's an empirical question. You have to go out and measure it. Think about what a radical statement that was. For 2,000 years, geometry had been considered a branch of pure logic, something you could work out from axioms in an armchair. And here was Riemann saying no. The geometry of the actual universe is something you discover through experiment, like the boiling point of water or the charge of an electron. Space might be flat. Space might be curved. Space might even have more than 3 dimensions. You won't know until you look. Now Gauss was in the audience that day. He was old and frail, and he rarely showed enthusiasm for anything anymore. But according to accounts from people who were there, Gauss was visibly moved by Riemann's lecture. He told a colleague afterward that the lecture exceeded his expectations, which from Gauss was about the highest praise imaginable. Gauss himself had privately explored non-Euclidean geometry decades earlier, but had never published his results, reportedly because he feared the controversy. He recognized in Riemann's work something he had glimpsed but never fully articulated. Riemann's health was never good. He suffered from tuberculosis for most of his adult life, and he spent his final years in Italy, seeking warmer climates, trying to outrun a disease that was slowly consuming him. He died in 1866 in Salaska, on the shores of Lake Maggiore, at 39. He left behind a relatively small body of published work, but nearly every piece of it was revolutionary. His lecture on geometry was published posthumously, and it slowly made its way through the mathematical world, where it detonated like a quiet bomb. Because here's what Riemann had really done. He hadn't just said that higher dimensions were possible. He'd given mathematicians a precise, rigorous language for talking about them. Before Riemann, a 4th dimension was a vague notion, an extra coordinate in an equation, a philosophical curiosity, a parlor trick for confusing your friends. After Riemann, it was a concrete, mathematical object with well-defined properties. You could calculate distances in it. You could measure curvature in it. You could do geometry in it, real geometry, with theorems and proofs and measurable quantities. The 4th dimension wasn't a metaphor anymore. It was a place, or at least a mathematically coherent description of a place. And this is where something wonderful happened, something that shows how ideas from pure mathematics can ripple outward into culture in unexpected ways. Because in the decades after Riemann's lecture, higher dimensions didn't just stay locked up in university mathematics departments. They escaped. They seeped into art, literature, philosophy, even spiritualism. The late 19th century saw an explosion of popular fascination with the 4th dimension, and the story of how that happened involves one of the most charming and enduring works of mathematical fiction ever written. A little book published in 1884 by a London schoolmaster named Edwin Abbott, and yes, that's his real name, with Abbott appearing twice. The book was called Flatland, a romance of many dimensions, and if you haven't read it, it's one of those books that changes the way you think about the world permanently. Abbott wasn't a mathematician. He was a theologian and educator, the headmaster of the City of London School. But he had a gift for analogy, and he understood something crucial about the problem of higher dimensions, namely, that the biggest obstacle isn't mathematical. It's imaginative. We can't picture a 4th spatial dimension because our brains evolved in 3 dimensions and our visual cortex literally doesn't have the wiring for it. So Abbott decided to attack the problem sideways. Instead of trying to make you imagine the 4th dimension directly, he asked you to imagine how a 2-dimensional creature would struggle to comprehend the 3rd dimension. And then he let you draw the parallel yourself. Flatland is narrated by a square, literally a geometric square, who lives in a 2-dimensional world. His entire universe is a flat plane. He can move north, south, east, and west, but he has no concept of up or down. He can't even imagine what up would mean. And then one day, a sphere visits him from the 3rd dimension. The sphere passes through Flatland, and from the square's perspective, all he sees is a circle that appears out of nowhere, grows larger, then shrinks and vanishes. He can't see the sphere as a sphere, because he has no access to the dimension that would let him perceive its full shape. The sphere tries to explain the 3rd dimension to him, and the square simply cannot grasp it, until the sphere physically lifts him out of Flatland and into 3-dimensional space, and suddenly, for the first time, the square can look down at his own world from above, seeing the insides of houses, the interiors of his fellow shapes, everything laid bare from a perspective that was literally inconceivable to him moments before. It's a gorgeous thought experiment, and it works on multiple levels. Because once you've felt the square's confusion and then his revelation, you can't help but wonder, what if we're the square? What if there's a dimension right next to us, perpendicular to everything we know, and we simply can't perceive it because we're trapped in our 3-dimensional slice of something larger? What would a 4-dimensional being see when it looked at us? It would see our insides. It could reach into a locked safe without opening it, just as you could reach into a circle drawn on a piece of paper without crossing the line, simply by coming at it from above. It could see every side of every object simultaneously, the way you can see every edge of a square drawn on paper all at once. And this is where Abbott's little book connects back to something Mobius noticed decades earlier, that business about mirror images. Remember the left hand and the right hand? In Flatland, there's a version of the same puzzle. A 2-dimensional creature shaped like the letter R cannot be turned into its mirror image within Flatland, but lift it into the 3rd dimension, flip it over, and set it back down. And suddenly, it's reversed. Abbott didn't invent this idea, but he dramatized it in a way that made it visceral and immediate. And the book sold remarkably well. It went through multiple editions and sparked a wave of popular writing about the 4th dimension that would continue for decades. But Flatland was just the most famous expression of a much broader cultural phenomenon. In the 1870s and 1880s, the 4th dimension became something of a craze. Mathematicians like William Kingdon Clifford, who was one of the first English-speaking thinkers to really absorb Riemann's ideas, gave public lectures arguing that space might actually be curved, that what we perceive as physical forces might really be manifestations of the geometry of higher dimensional space. Clifford was brilliant and charismatic, and he died young too, at 33, of tuberculosis, just like Riemann. There's something haunting about how many of these visionaries were taken so early. But Clifford's popular writings helped bring Riemann's abstract mathematics to a wider audience, and they planted ideas that would germinate in some truly unexpected places. Clifford had this way of putting things that made you feel like the ground beneath your feet was slightly less solid than you'd assumed. He wrote an essay in 1870 called On the Space Theory of Matter, and in it he proposed, and I want you to really sit with this, that the motion of matter through space might be nothing more than a variation in the curvature of space itself. That matter isn't a thing sitting in space. It is space bent. He was 30 years old when he wrote that. Einstein wouldn't publish general relativity for another 45 years, and Clifford didn't have the mathematical machinery to turn this intuition into a full theory. That would require tools Riemann had only begun to sketch. But the instinct was extraordinary. He was reaching towards something real, something that would eventually reshape our entire understanding of gravity, of cosmology, of the fabric of the universe. And then he was gone, 33 years old, leaving behind a young wife, 2 small daughters, and a handful of papers that most physicists wouldn't fully appreciate for decades. But the cultural momentum he helped create didn't die with him. Not at all. By the 1880s and 1890s, the fourth dimension had escaped the lecture halls and the mathematics journals and had seeped into art, literature, philosophy, even spiritualism. And that last one, spiritualism, is worth pausing on, because it's one of the stranger chapters in this whole story. There was a German astrophysicist named Johann Carl Friedrich Zollner, a legitimate scientist at the University of Leipzig, who became convinced that the phenomena reported by spirit mediums, objects appearing inside sealed containers, knots tying themselves in closed loops of rope, could be explained by the existence of a fourth spatial dimension. His reasoning, on the surface, wasn't entirely crazy. Think about it the way Abbott would have. If a 3-dimensional being reached into flatland, the 2-dimensional inhabitants would see objects appearing and disappearing with no apparent cause. A sphere passing through their plane would look like a circle that materialized from nothing, grew, shrank, and vanished. From the flatlander's perspective, that would look like magic. So Zollner argued that maybe spirit mediums were somehow accessing a fourth spatial dimension, and the seemingly impossible things they did were just ordinary actions performed in a direction we can't perceive. In 1877 and 1878, Zollner conducted a series of experiments with an American medium named Henry Slade. He asked Slade to tie knots in a loop of cord whose ends were sealed together, something that's topologically impossible in 3 dimensions but trivially easy in 4. And Slade apparently succeeded. Zollner published the results and declared them proof of the 4th dimension's physical reality. Now here's the thing. Most of the scientific community was not impressed. Slade had already been convicted of fraud in England. The experiments were poorly controlled. Other scientists who attended the sessions reported obvious sleight of hand. Zollner's reputation suffered enormously, and the whole episode became a cautionary tale about what happens when a real scientific idea gets tangled up with wishful thinking. But it's fascinating precisely because it shows how powerful the concept of higher dimensions had become in the popular imagination. The 4th dimension wasn't just a mathematical abstraction anymore. People were asking whether it was real, whether it was out there, whether it could explain things that seemed otherwise inexplicable. And while the spiritualists were chasing ghosts in the 4th dimension, something much more interesting was happening in mathematics. Because mathematicians were getting very comfortable working in higher dimensional spaces, and they were discovering that these spaces had genuine, surprising properties that you couldn't predict just by extrapolating from 3 dimensions. Let me give you an example that I think is really beautiful. Think about a sphere. You know what a sphere looks like: a ball, the surface of the Earth, an orange. In mathematics, a sphere is defined as all the points that are the same distance from a center point. In 2 dimensions, that gives you a circle. In 3 dimensions, a sphere. But you can write the same definition using 4 coordinates, or 5, or 100, and you get what mathematicians call hyperspheres. And here's something genuinely strange about them. The volume of a unit hypersphere, that's a hypersphere with radius 1, increases as you add dimensions, but only up to a point. It peaks somewhere around 5 dimensions, and then it starts shrinking. By the time you get to very high dimensions, the volume of a unit hypersphere is essentially 0. Almost all the space in a high-dimensional cube is concentrated in the corners, not in the center. The sphere becomes vanishingly small compared to the box that contains it. That's deeply counterintuitive. You'd think more dimensions means more room, and in some sense it does. But the geometry behaves in ways that violate your 3-dimensional instincts. And this isn't just a curiosity. It matters enormously in modern statistics, machine learning, data science, any field where you're working with data that has many variables. Each variable is a dimension, and in high-dimensional spaces, the data behaves in ways that seem paradoxical until you understand the geometry. Almost all the data points in a high-dimensional dataset end up near the edges of whatever region you're looking at, not near the center. This is called the curse of dimensionality, and it's one of the fundamental challenges of working with complex data. But we're getting ahead of ourselves. That's a 20th and 21st century concern. Let's stay in the late 1800s for a bit longer, because the story is about to take a turn that changes everything. By the 1890s, there was a growing sense among physicists that something was not quite right with the classical picture of the universe. Newtonian mechanics worked beautifully for everyday objects, cannonballs, planets, pendulums, but there were cracks appearing at the edges. The orbit of Mercury didn't quite match Newton's predictions. There was a tiny discrepancy, a precession of Mercury's perihelion, the point in its orbit closest to the Sun, that couldn't be explained by the gravitational pull of the other planets. It was small, about 43 arc-seconds per century, which sounds like almost nothing. But astronomers could measure it, and it stubbornly refused to go away. Some people proposed a hidden planet, which they called Vulcan, orbiting closer to the Sun than Mercury. Others suggested modifications to Newton's law of gravity. Nobody could make it work. And then there was the problem of light. James Clerk Maxwell had shown in the 1860s that light was an electromagnetic wave, and his equations predicted that it should travel at a specific speed, about 186,000 miles per second, regardless of how the source or the observer was moving. That was strange. If you're on a train and you throw a ball forward, the ball's speed relative to the ground is the train's speed plus the throw speed. But Maxwell's equation said light didn't work that way. Light always traveled at the same speed, period. In 1887, Albert Michelson and Edward Morley performed their famous experiment trying to detect the Earth's motion through the supposed luminiferous ether, the medium that light waves were thought to travel through, and found nothing. No motion. No ether wind. The speed of light was the same in every direction, no matter how the Earth was moving. This was deeply puzzling, and physicists spent years trying to reconcile it with Newtonian physics. Hendrik Lorentz and George Fitzgerald independently proposed that objects moving through the ether physically contracted in the direction of motion, just enough to explain the null result. Lorentz developed a set of mathematical transformations, the Lorentz transformations, that described how measurements of space and time would differ between observers moving at different velocities. And these transformations had a very interesting property. They mixed up space and time. The time measured by one observer depended on both the time and the position measured by another observer, and vice versa. Space and time were not separate, independent things in these equations. They were entangled. And then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that reframed the entire situation. You know his name, Albert Einstein. His paper, On the Electrodynamics of Moving Bodies, introduced what we now call special relativity, and it started from two simple postulates. First, the laws of physics are the same in all inertial reference frames, meaning, if you're moving at a constant velocity, no experiment you can do will tell you whether you're moving or standing still. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion. That's it. Two postulates, and from those two starting points, using nothing more than algebra and clear thinking, Einstein derived all the Lorentz transformations. He showed that time dilation and length contraction weren't ad hoc fixes. They were inevitable consequences of the nature of light and motion. But here's what matters for our story about dimensions. Einstein's special relativity revealed that space and time are not separate things. They're aspects of a single entity. And it was Einstein's former mathematics professor, Hermann Minkowski, who made this explicit in the most dramatic way possible. In 1908, Minkowski gave a lecture at the University of Cologne that opened with one of the most famous declarations in the history of physics. He said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Think about what that means. For all of human history, space was space and time was time. Three dimensions of space, left, right, forward, back, up, down, and one dimension of time, ticking along independently. Minkowski said no. There are four dimensions, and they're woven together into a single fabric that he called space-time. And this wasn't just a philosophical statement. He gave it precise mathematical form. In Minkowski's space-time, you can describe any event, anything that happens, by four numbers, 3 spatial coordinates and 1 time coordinate. And the distance between two events isn't measured the way you'd measure distance in ordinary space. There's a new kind of distance, called the space-time interval, and it treats the time dimension slightly differently from the spatial dimensions. There's a minus sign in the formula. If you measure the spatial separation between two events and call it delta x, delta y, delta z, and the time separation delta t, the space-time interval is the speed of light squared times delta t squared minus delta x squared minus delta y squared minus delta z squared. That minus sign, or rather, the difference in sign between the time part and the space parts, is what makes space-time fundamentally different from ordinary four-dimensional space. It's what gives the universe its causal structure, its distinction between past and future, its speed limit. And here's where Riemann's ghost enters the room. Because Minkowski's space-time is exactly the kind of mathematical space Riemann had described in his 1854 lecture. It's a manifold, a space that can be described by coordinates, equipped with a metric, a rule for measuring distances. The metric of Minkowski spacetime is simple and flat, like a perfectly smooth tabletop extended into 4 dimensions. But Einstein wasn't done. He spent the next 10 years, from 1905 to 1915, struggling with the problem of gravity, and when he finally solved it, the answer was pure Riemann. General relativity says that gravity isn't a force at all, it's curvature. Massive objects bend space-time around them, and other objects follow the curved paths, called geodesics, through that bent spacetime. The Earth doesn't orbit the Sun because an invisible force pulls it. The Earth orbits the Sun because the Sun's mass warps the four-dimensional spacetime around it, and the Earth follows the straightest possible path through that curved geometry. And the mathematical language Einstein used to describe this curvature was Riemann's. The metric tensor, the curvature tensor, the whole apparatus of differential geometry that Riemann had invented for purely mathematical reasons 60 years earlier. Einstein needed every bit of it. And remember Clifford? That young Englishman who died at 33, who had written that matter might be nothing more than curved space? Einstein's general relativity was, in a very real sense, the fulfillment of Clifford's vision. Matter tells space-time how to curve, and curved space-time tells matter how to move. That's the whole theory, in one sentence, and it explained Mercury's orbit perfectly. Those 43 arcseconds per century of anomalous precession fell right out of the equations. No hidden planet needed, just geometry, just the curvature of four-dimensional space-time around the Sun. So by 1915, the fourth dimension wasn't a parlor trick or a spiritualist fantasy or a mathematical curiosity. It was the architecture of reality. And almost immediately, people started asking the obvious next question. If the universe has four dimensions, and the fourth one turned out to be physically real and essential for understanding gravity, then what about a fifth dimension? What if there were more dimensions hiding somewhere, curled up or stretched out in some direction we couldn't see? What if the geometry of the universe was even richer than Einstein had realized? And here's the thing. Someone asked that question almost immediately. His name was Theodor Kaluza, and he was a relatively obscure German mathematician working at the University of Königsberg. Not a famous figure. Not someone with a big research group or a prestigious chair. Just a quiet, deeply thoughtful man who happened to have one of the most audacious ideas in the history of physics. And the story of how he came to it is wonderful, because it's one of those moments where someone does something that seems almost unreasonably bold, and it works. Or at least, it half works, which in physics is sometimes even more tantalizing than a clean success. So picture Kaluza in 1919. The First World War has just ended. Germany is in turmoil, and Kaluza is sitting at his desk, probably late at night. His son later recalled that his father did his best thinking in the evenings, which feels appropriate for us right now. And he's playing with Einstein's equations of general relativity. He knows the equations beautifully. He understands how the metric tensor works in four-dimensional spacetime, how it encodes the curvature that produces gravity. And then he asks himself a question that sounds almost childishly simple. What if I just add one more dimension? What if, instead of writing the metric tensor for a four-dimensional spacetime, I write it for a five-dimensional spacetime? What happens to the equations? Now, you might think that adding a dimension would just make everything more complicated without giving you anything new. More variables, more equations, more mess. But that's not what happened. What happened was something that reportedly made Kaluza stand up from his desk in shock. When he wrote out Einstein's field equations in 5 dimensions instead of 4, the equations naturally split into 3 groups. One group was exactly Einstein's equations of general relativity, gravity, in 4-dimensional space-time, just as Einstein had described it. Another group was exactly Maxwell's equations of electromagnetism, the equations that describe light, electric fields, magnetic fields, everything that Maxwell had unified back in the 1860s. And the third group was a leftover equation involving a scalar field that nobody quite knew what to do with at the time. Think about what that means. For decades, physicists had known about two fundamental forces, gravity and electromagnetism. They seemed completely different. Gravity was about mass and curved spacetime. Electromagnetism was about charges and fields. Einstein himself had spent years trying to find a way to unify them, to show that they were somehow two aspects of the same underlying thing. And here was Kaluza saying, they already are unified. You just can't see it because you're only looking at 4 dimensions. If the universe actually has 5 dimensions, then gravity and electromagnetism are both just geometry. They're both curvature. They're just curvature in different directions of a 5-dimensional space-time. That is wild. And Kaluza knew it was wild. He wrote up his paper and sent it to Einstein in 1919, asking Einstein to help him get it published. And Einstein's reaction is fascinating. He sat on the paper for 2 years, 2 full years. He wrote back to Kaluza saying the idea was interesting, then went quiet, then wrote again saying he liked it more, then went quiet again. It wasn't until 1921 that Einstein finally recommended the paper for publication. And you can understand his hesitation, right? The mathematics was beautiful. The unification was elegant. But there was this enormous, unavoidable question. If there's a 5th dimension, where is it? Why can't we see it? Why can't we move in that direction? Kaluza's original answer was essentially to just declare, by fiat, that nothing depends on the 5th dimension. He imposed what's called the cylinder condition. He said, look, all the physics we observe is independent of position along this 5th dimension, so it's there mathematically, but it doesn't show up in our measurements, which is not entirely satisfying, right? It's a bit like saying there's an extra room in your house, but the door is permanently sealed and nothing that happens in there affects anything out here. Okay, but then why believe the room exists? And this is where a Swedish physicist named Oscar Klein enters the story, about 5 years later. And his contribution is genuinely beautiful. Klein was working in the mid-1920s, right when quantum mechanics was being born. Heisenberg and Schrödinger and Bohr were all revolutionizing physics at the same time. And Klein brought quantum thinking to Kaluza's 5th dimension. His idea was this: the 5th dimension is real. It's a physical direction you could in principle move in, but it's curled up, rolled up into a tiny, tiny circle. So tiny that you could never notice it. Let me give you an analogy because this is one of those ideas that really benefits from one. Think about a garden hose. If you look at a garden hose from far away, say, from across a football field, it looks like a one-dimensional line. It's just a long, thin thing. You'd say it has one dimension, length. But if you walk up close, you realize it also has a circular dimension wrapping around it. An ant crawling on the surface of that hose can move in 2 directions, along the length of the hose or around the circumference. From far away, you only see the one big dimension. The tiny circular dimension is there, but it's too small to notice at a distance. Klein said the 5th dimension is like that circumference. It's there at every point in our 4-dimensional spacetime, but it's curled up into a circle so unimaginably small, on the order of the Planck length, about 10 to the minus 35 meters, that no experiment could ever directly detect it. You can't see it, you can't probe it, You can't send anything into it in any measurable way. But its existence has consequences, because if a quantum particle, say an electron, exists in this five-dimensional space-time, then it has a wave function that extends into the fifth dimension too. And because the fifth dimension is a circle, the wave function has to be periodic. It has to come back to the same value after going around the circle. That means only certain wavelengths fit. Only certain modes are allowed. And those allowed modes, when you project them back down into our four-dimensional world, look like particles with quantized electric charge. So here's the kicker. In Kaluza-Klein theory, electric charge is momentum in the fifth dimension. The reason charge comes in discrete units, the reason you can't have half an electron's charge, is the same reason a vibrating guitar string can only produce certain harmonics. The boundary conditions force quantization. The geometry of the curled-up dimension determines the physics we observe. Now, you might be lying there thinking, okay, this is elegant, this is clever, but does it actually work? And the honest answer is, sort of. Kaluza-Klein theory, in its original form, has some real problems. It predicts a scalar field, that leftover third piece of the equations, that doesn't quite match observation. It doesn't account for the nuclear forces, the strong and weak forces that were discovered in the 20th century. And the predicted mass of the lightest charged particles doesn't match the electron mass. So, as a complete theory of physics, it falls short. But here's what's really important about Kaluza-Klein. It established an idea. It planted a seed that would grow for the rest of the century. The idea that extra dimensions could be physically real but hidden, and that the geometry of those hidden dimensions could determine the fundamental forces and particles we observe. That is a staggeringly powerful idea, and it never went away. Einstein himself kept coming back to it, spending much of his later career trying to make higher dimensional unification work. He never succeeded. His unified field theory efforts are generally considered a dead end, but the core insight of Kaluza and Klein was sound. The execution was just premature. The tools weren't ready yet, and the tools wouldn't be ready for decades because first, physics had to reckon with the quantum revolution. Through the 1920s, 30s, and 40s, the focus shifted away from geometry and toward quantum field theory. Physicists learned to describe particles as excitations of quantum fields. They built quantum electrodynamics, QED, which described the electromagnetic force with breathtaking precision. They discovered the strong nuclear force that holds atomic nuclei together, and the weak nuclear force responsible for certain kinds of radioactive decay. By the 1970s, 3 of the 4 fundamental forces had been successfully described by quantum field theories, unified into what's called the standard model of particle physics. Gravity was the holdout. General relativity described gravity beautifully at large scales, planets, stars, galaxies, but when you tried to apply quantum mechanics to gravity, the math exploded. You got infinities everywhere. Nonsensical answers. The 2 greatest theories of the 20th century, general relativity and quantum mechanics, were fundamentally incompatible. And this is the crisis that would eventually bring extra dimensions roaring back into mainstream physics. Because in the late 1960s and early 1970s, a new kind of theory began to emerge, one that didn't start from particles at all, but from something else entirely, something that would require not 5 dimensions, not 6, but 10, or 11, or 26, depending on which version you were working with. It started, as so many breakthroughs do, with a puzzle that seemed completely unrelated. In 1968, a young Italian physicist named Gabriele Veneziano was trying to understand the strong nuclear force, the force that holds quarks together inside protons and neutrons. The strong force was notoriously difficult. Unlike electromagnetism, which gets weaker as particles move apart, the strong force actually gets stronger with distance, which is why you can never isolate a single quark. Veneziano was looking for a mathematical formula that could describe how strongly interacting particles scatter off each other, and he found one, almost by accident, in an old mathematics textbook. It was the Euler beta function, a formula that Leonhard Euler had written down in the 18th century for purely mathematical reasons, and it fit the scattering data remarkably well. But nobody understood why. Why would an 18th century mathematical function describe nuclear physics? What was the underlying physical picture? And it took about 2 years for physicists to figure out the answer. In 1970, Yoichiro Nambu in Chicago, Holger Beck Nielsen in Copenhagen, and Leonard Susskind in New York all independently realized what Veneziano's formula was actually describing. It wasn't describing particles at all. It was describing strings, tiny, one-dimensional vibrating filaments of energy. If you imagined that the fundamental constituents of matter weren't point particles, but tiny vibrating strings, then the way those strings vibrated and interacted naturally produced Veneziano's formula. The different vibrational modes of the string corresponded to different particles, just like the different vibrational modes of a violin string correspond to different musical notes. And this was the birth of string theory. But here's where it gets strange, and here's where our story about dimensions takes its most dramatic turn. When Nambu and Susskind and others started working out the mathematics of these vibrating strings, they discovered something deeply unsettling. The equations only worked. They were only mathematically consistent, free of certain fatal anomalies, if the strings vibrated in a very specific number of dimensions, not 4, not 5. For the original version, called bosonic string theory, the number was 26. 26 dimensions of spacetime. And when a more refined version called superstring theory was developed in the early 1980s, incorporating a beautiful symmetry called supersymmetry that relates matter particles to force particles, the required number dropped, but only to 10. 10 dimensions, 9 of space and 1 of time. Now, you might reasonably ask, how can a theory that requires 10 dimensions possibly describe our universe, which very clearly has 3 dimensions of space and 1 of time? And this is exactly where Kaluza-Klein's old idea came back with a vengeance. Because the answer string theorists gave was the same answer Klein had given back in 1926. The extra dimensions are there, but they're curled up so small you can't see them. They're compactified, rolled up tight at every single point in space, forming a tiny hidden geometry far too small for any experiment to detect directly. But here's the thing, and this is what makes it so much more interesting than Klein's original idea. Klein only had to hide 1 extra dimension. 1. And he rolled it into a simple circle. String theory needs to hide 6 extra dimensions. 6. And you can't just roll 6 dimensions into 6 separate circles and call it a day. Well, technically, you can, and people did try that, and it's called toroidal compactification, folding the extra dimensions into a 6-dimensional torus, which is basically the higher dimensional equivalent of a donut. But it turns out that doesn't give you the right kind of physics. The resulting four-dimensional world you'd see doesn't look anything like ours. The particles come out wrong. The symmetries are wrong. It's too simple, too symmetric. The real universe is messy and specific, and you need a messier, more specific kind of hidden geometry to produce it. So the question became, what shape do the extra 6 dimensions need to be? What geometry, curled up at every point in our familiar four-dimensional spacetime, would give rise to the particles and forces we actually observe? And this is where some genuinely beautiful mathematics enters the picture. In the mid-1980s, a group of physicists, Philip Candelas, Gary Horowitz, Andrew Strominger, and Edward Witten, showed that for superstring theory to work properly, for it to preserve just the right amount of supersymmetry in the 4 large dimensions we experience, the 6 compact dimensions need to form a very particular type of geometric object called a Calabi-Yau manifold. Now, let's slow down on that name, because it sounds intimidating, but the idea behind it is actually kind of lovely. A Calabi-Yau manifold is named after 2 mathematicians. Eugenio Calabi, an Italian-American mathematician, conjectured in 1954 that a certain class of geometric spaces should exist, spaces that are compact, complex, and have a very specific property related to their curvature. Think of it this way. These are shapes that, despite being incredibly intricate and curved in complicated ways, have a kind of overall flatness to them. Their average curvature, in a precise mathematical sense called Ricci flatness, is 0. Calabi proposed that such spaces should exist, but he couldn't prove it. That proof came over 2 decades later, in 1978, from Xingtung Yau, a Chinese-American mathematician who would go on to win the Fields Medal partly for this work. Yau showed rigorously that, yes, these spaces Calabi imagined actually do exist, and they exist in abundance. So a Calabi-Yau manifold is a space that satisfies Calabi's conjecture as proven by Yau. And what Candelas, Horowitz, Strominger, and Witten showed in 1985 is that if you take 10-dimensional spacetime and you let 6 of those dimensions curl up into a Calabi-Yau manifold, you get a 4-dimensional world that has exactly the right mathematical structure to potentially describe our universe. The specific shape of the Calabi-Yau manifold, its topology, its holes, its twists, its detailed geometry, determines what particles exist in the 4-dimensional world, what masses they have, how many generations of matter there are, what symmetries govern their interactions. The physics we observe would be, in a very deep sense, a reflection of the geometry of these hidden dimensions. Think about what that means for a second. It's Riemann's dream taken to its most radical extreme. Remember Riemann back in 1854, standing in front of Gauss, arguing that the properties of space, its curvature, its shape, might be the thing that explains physical phenomena? That geometry isn't just the stage on which physics plays out, but is itself the substance of physics. String theory says exactly that. The reason you see an electron with a particular charge and mass, the reason the strong force behaves differently from electromagnetism, the reason there are 3 generations of quarks, all of it, potentially, comes from the shape of 6 dimensions you can never directly see. And here's where it gets both exciting and deeply problematic, because there isn't just one Calabi-Yau manifold. There are many, enormously, absurdly many. At first, mathematicians thought there might be a handful, maybe a few dozen. But as the classification efforts progressed through the late 1980s and 1990s, the number kept growing. Tens of thousands of distinct Calabi-Yau threefolds were constructed. and each one gives you a different version of four-dimensional physics. Different particles, different forces, different constants of nature. And it gets worse, because even for a single Calabi-Yau manifold, there are additional choices you can make. How strings wrap around various holes and cycles in the geometry, what fluxes thread through different surfaces. When you account for all of these choices, the number of possible configurations explodes to something almost incomprehensible. Estimates vary, but a commonly cited figure, coming from work by Raphael Busso and Joseph Polchinski around 2000, and later elaborated by others, is something like 10 to the 500th power. That's a 1 followed by 500 zeros. 500 zeros. For comparison, the number of atoms in the observable universe is roughly 10 to the 80th. So the number of possible string theory landscapes is not just large, it's large in a way that makes every other large number you've ever encountered feel quaint. This collection of possibilities is called the string theory landscape, and it represents one of the deepest puzzles, some would say crises, in modern theoretical physics. Because if string theory can produce 10 to the 500 different versions of physics, and we only observe one version, our version, with our particular particles and our particular constants, then how do you figure out which point in the landscape corresponds to our universe? How do you make a prediction? Some physicists see this as a fatal flaw. If a theory can predict essentially anything, it predicts nothing. It's not falsifiable in the traditional sense. You can't do an experiment and say, string theory predicted this number and the experiment confirmed it, because string theory, as it stands, doesn't predict specific numbers without first knowing which Calabi-Yau manifold and which flux configuration to use. And there's no known principle, no selection rule, that tells you which one to pick. It's a bit like having a theory that says the speed of light could be any value, and then claiming success when you measure it to be what it is. That's not really a prediction. Others, though, see the landscape differently. Some physicists, Leonard Susskind prominent among them, have embraced what's called the anthropic approach. The idea is that maybe all of these different configurations are actually realized. Maybe there's a vast multiverse of regions, each with different compactifications, different physics, different constants, and we find ourselves in this particular one not because it's special or preferred by the mathematics, but simply because it's one of the ones compatible with the existence of complex structures, chemistry, stars, planets, and ultimately observers like us. It's a deeply controversial idea. It feels, to many physicists, like giving up on the dream of deriving the laws of physics from first principles, but to others, it feels like an honest reckoning with what the mathematics is telling us. And here's where I want to pause and acknowledge something, because this is a genuine, unresolved debate in physics right now. This isn't settled. There are brilliant people on both sides, and the argument has been going on for over 20 years with no clear resolution. Some string theorists are working hard to find additional mathematical constraints that might narrow the landscape, that might show that most of those 10 to the 500 possibilities are actually inconsistent when you look more carefully, that they're in what's called the swampland rather than the landscape, meaning they look like valid solutions, but actually can't be realized in a consistent theory of quantum gravity. This swampland program, pioneered significantly by Kamran Vafa at Harvard starting around 2005, is an active and fascinating area of research. The hope is that the swampland conditions are restrictive enough to winnow the landscape down to something manageable, maybe even to a unique solution. But that hope hasn't been realized yet. So let's sit with that for a moment. String theory tells us that the universe might have 10 dimensions, 6 of them curled up into a Calabi-Yau manifold, whose specific shape determines everything about the physics we observe. But the theory doesn't tell us which shape. It offers a staggering number of possibilities and, at least so far, no way to choose among them. It's as if someone handed you a key that opens every lock in the world and said, "See, it works." Well, yes, but that's not quite what we were hoping for. But the story of extra dimensions in physics didn't stop with this puzzle. Something remarkable happened in 1995 that changed the entire landscape of string theory itself. Not the landscape of solutions, but the conceptual landscape, the way physicists understood what string theory actually is. And it happened at a conference at the University of Southern California when Edward Witten, who by this point was widely regarded as the most brilliant theoretical physicist of his generation, stood up and proposed something that stunned the room. Because it turned out that there weren't just 10 dimensions in the picture. There were 11. And the 5 different versions of string theory that had been developed over the previous decade, 5 seemingly distinct competing theories, each consistent in 10 dimensions but each different from the others, were not actually different theories at all. They were all different limits, different perspectives, different corners of a single, deeper, 11-dimensional theory that Witten called M-theory. And nobody, including Witten himself, was entirely sure what the M stood for. He suggested it could stand for master, or mother, or membrane, or even mystery. That ambiguity was deliberate, because the theory he was pointing toward didn't yet have a complete formulation. It was more like a shadow on the wall. You could see its outline. You could tell it was something enormous, but you couldn't quite make out all its features. And yet, the evidence that it was real, that this 11-dimensional framework existed, and that all 5 string theories were just different windows into it, was compelling enough to shift the entire field almost overnight. Let me explain why this was so surprising. Throughout the late 1980s and early 1990s, string theorists had been working with 5 distinct versions of the theory. They had names: Type 1, Type 2A, Type 2B, and then 2 versions of something called heterotic string theory, one based on a mathematical structure called SO32, and the other on E 8 times E8. Each of these theories was internally consistent. Each required 10 dimensions. Each described strings vibrating in spacetime. But they differed in important ways. The types of strings they allowed, whether those strings were open with loose ends or closed into loops, the symmetry groups that governed their interactions. And for years, this multiplicity was a genuine embarrassment. If string theory was supposed to be the unique, ultimate theory of everything, why were there 5 of them? That's like saying, "You've found the one true answer. And by the way, here are 4 other equally valid answers." What Witten showed, building on work by several other physicists, including Chris Hull, Paul Townsend, Joe Polchinski, and others, was that these 5 theories were connected by a web of mathematical relationships called dualities. And here's where it gets really beautiful. A duality, in this context, means that 2 theories that look completely different on the surface are actually describing the same physics, just from different vantage points. Imagine you're standing on one side of a mountain, and I'm standing on the other. We'd describe completely different landscapes, different trees, different rivers, different views. But we're looking at the same mountain. Dualities are like that. They're exact equivalences between theories that seem unrelated. One type of duality, called T-duality, connects a string theory with one of its extra dimensions curled into a very small circle to another string theory with that dimension curled into a very large circle. Think about what that means. If you take type 2 A string theory and make one of its compact dimensions incredibly tiny, the physics you get is identical. Not approximately, but exactly identical to type 2b string theory with that dimension made incredibly large. Small and large become interchangeable. The theory can't tell the difference. That's a profoundly strange statement, and it hints at something deep about the nature of space itself in string theory. Below a certain scale, the very concept of distance starts to lose its meaning. Another type, called S-duality, connects a theory at strong coupling, where the strings are interacting very intensely, to another theory at weak coupling, where interactions are gentle and calculations are tractable. This was especially powerful because physicists can usually only do calculations when the coupling is weak. When interactions get strong, the math becomes intractable. But S-duality says that the strong coupling limit of one theory is just the weak coupling limit of another. So if you can't solve your problem in one theory because the coupling is too strong, you translate it into the dual theory where the coupling is weak, and suddenly you can calculate. And when Witten and others mapped out all these dualities, they found that the 5 string theories and one more thing. 11-dimensional supergravity, a theory that had been developed back in the late 1970s and early 1980s, and then largely set aside, were all connected. They formed a hexagonal web, with each theory sitting at a corner and dualities linking them together. And at the center of that web, at the place where all the dualities converged, was this mysterious 11-dimensional theory, M-theory. Now, that 11th dimension is worth pausing on. For years, string theorists had been adamant that the theory required exactly 10 dimensions, 9 of space and 1 of time. Where did this 11th dimension come from? The answer involves the strong coupling behavior of type 2A string theory. As you crank up the coupling strength in type 2A, something unexpected happens. A new dimension of space literally opens up. The strings, which you thought were one-dimensional, start to look like they have thickness. That thickness is the 11th dimension, and at strong coupling, it becomes just as large and important as the other 10. The 10-dimensional theory was really an 11-dimensional theory all along, but you could only see all 11 dimensions when the coupling was strong enough. And in 11 dimensions, the fundamental objects aren't just strings anymore. They're membranes, 2-dimensional surfaces, like sheets, flapping around in 11-dimensional spacetime. These are called M2 branes, and there are also 5-dimensional objects called M5 branes. When you compactify that 11th dimension, curl it up small, the membranes wrap around it and look like strings from the 10-dimensional perspective. So strings, it turned out, weren't truly fundamental. They were membranes seen edge-on, like looking at a garden hose from so far away that it looks like a line. This is where Joe Polchinski's work became crucial. In 1995, the same year as Witten's announcement, Polchinski showed that string theory naturally contained objects called D-branes, higher dimensional surfaces on which open strings could end. The D stands for Dirichlet, after the boundary conditions that fix the string endpoints to the brane. And these weren't just mathematical curiosities. D-branes turned out to be dynamical objects in their own right. They could move, vibrate, carry charge, and interact with each other. And they came in various dimensionalities. D0 branes were points, D1 branes were strings, D2 branes were membranes, and so on, all the way up to D9 branes that filled all 9 spatial dimensions. Here's what's really clever about this. In certain configurations, the particles of the standard model, the quarks, the electrons, the photons, could be understood as open strings whose endpoints are stuck on a particular D brane. Our entire observable universe, in this picture, might be a 3-dimensional D brane, a D3 brane, floating in a higher dimensional space. We can't perceive the extra dimensions, not because they're too small necessarily, but because we're stuck. We're like insects crawling on a sheet of paper, unable to jump off into the room around us. Gravity, being a property of the spacetime itself, rather than of open strings on a brane, could leak into the extra dimensions. But light, matter, the strong and weak forces, all of those would be confined to our brain. This idea, which was developed extensively in the late 1990s by Lisa Randall and Raman Sundram, among others, offered a completely different approach to the extra dimensions problem. Instead of curling the extra dimensions up to the Planck scale, roughly 10 to the minus 35 meters, where they'd be undetectable, you could potentially have large extra dimensions, even infinitely large ones, as long as the geometry of the higher dimensional space was warped in the right way. Randall and Sundram published 2 landmark papers in 1999. In one model, they showed that if you have 2 branes separated by a 5-dimensional anti-de Sitter space, a space with a specific kind of negative curvature, then the geometry naturally generates an exponential hierarchy between energy scales on the 2 branes. This was exciting because it offered a potential explanation for one of the deepest puzzles in physics: why gravity is so absurdly weak compared to the other forces. The ratio is staggering. Gravity is roughly 10 to the 36 times weaker than electromagnetism. In the Randall-Sundram picture, gravity isn't intrinsically weak. It's just diluted by the geometry of the extra dimension. On the other brane, gravity would be just as strong as the other forces. But by the time its effects warp across the bulk to reach our brane, they've been exponentially suppressed. Think about what that means for a second. The weakness of gravity, something you experience every time you pick up a coffee cup and effortlessly overcome the gravitational pull of the entire Earth, might be a geometric accident, a consequence of where we happen to live in a higher dimensional space. Their second model was even more radical. It showed that you could have a single brane in a 5-dimensional space, where the 5th dimension is actually infinite in extent, and yet gravity on the brane would still behave like normal 4-dimensional gravity at large distances. The extra dimension is infinite, but its effects are hidden by the curvature of the bulk. This was a genuine surprise. Everyone had assumed that extra dimensions had to be compact, curled up, and finite, to avoid contradicting observations. Randall and Sundram showed that wasn't necessarily true. Now, these brane world scenarios made specific predictions that could, in principle, be tested. If extra dimensions were large enough, you'd expect to see deviations from Newton's inverse square law of gravity at short distances. Experiments at the University of Washington, led by Eric Adelberger and his group, used incredibly sensitive torsion balance experiments to test gravity down to distances of about 50 micrometers. They found no deviations. That ruled out extra dimensions larger than that scale, but it didn't rule out the general idea. Other predictions involved the production of microscopic black holes at particle colliders. If extra dimensions brought the true scale of quantum gravity down low enough, the Large Hadron Collider at CERN might have enough energy to create tiny black holes that would evaporate almost instantly through Hawking radiation, producing distinctive sprays of particles. The LHC looked for these signatures after it began operations in 2010. They weren't found. That pushed the energy scale of extra dimensions higher, making them harder to access. But again, it didn't kill the idea outright. And this brings us to something important about where the physics of extra dimensions stands today in the broader scientific landscape. Because we've now traced this story from Riemann's abstract geometry in 1854, through Einstein's curved spacetime, through Kaluza-Klein's early attempts at unification, through the explosive development of string theory and M theory, through Calabi-Yau manifolds and the landscape problem, through brane worlds and experimental searches. And the honest truth is that as of now, there is no direct experimental evidence for extra dimensions. None. Not a single measurement, not a single particle, not a single gravitational anomaly that requires extra dimensions to explain. The extra dimensions of string theory remain, for the moment, a theoretical prediction without empirical confirmation. But, and this is a crucial but, that doesn't mean the ideas are wrong or useless or merely speculative fantasy. Because the mathematics of higher dimensions has proven extraordinarily fertile in ways that go far beyond the question of whether our particular universe happens to have 10 or 11 of them. And that might sound like a strange consolation prize. Oh, we didn't find the extra dimensions, but the math turned out to be useful. But honestly, when you look at what's happened over the last few decades, it's far more profound than that. The mathematics born from thinking about higher dimensional spaces has transformed entire branches of pure mathematics, condensed matter physics, quantum information theory, and even fields that seem to have nothing to do with strings or branes at all. It's one of the most surprising twists in this whole story. Let me give you a concrete example. In 1997, a theoretical physicist named Juan Maldacena, who was then at Harvard, proposed something that has arguably become the single most influential idea in theoretical physics in the last 30 years. It's called the ADS/CFT correspondence, and while the name sounds intimidating, the core idea is actually breathtaking in its elegance. What Maldacena showed, or more precisely, conjectured with overwhelming mathematical evidence, is that a theory of gravity in a higher dimensional space is exactly equivalent to a quantum field theory, without gravity, living on the boundary of that space. Let me say that again more slowly, because it's worth sitting with. Imagine you have a universe that's shaped like the inside of a can, a higher dimensional space with a boundary, a surface wrapping around it. Maldacena's conjecture says that everything happening inside that can, all the gravitational physics, all the warping of space-time, all the motion of objects through the interior, all of it can be perfectly described by a completely different theory that lives only on the surface of the can, a theory that doesn't even include gravity. The two descriptions are not approximately the same. They're exactly the same. Every question you can ask about the interior has a precise translation into a question about the surface, and vice versa. The specific setup Maldacena used involves something called anti-de Sitter space. That's the ADS part, which is a particular kind of negatively curved higher dimensional spacetime. Think of it as a spacetime shaped like a saddle that goes on forever, rather than the flat or gently curved spacetime we seem to live in. And on the boundary of this anti-de Sitter space, the equivalent theory is a conformal field theory. That's the CFT part, which is a special kind of quantum field theory with extra symmetry. The particular case Maldacena studied involved a 5-dimensional anti-de Sitter space times a 5-dimensional sphere, so 10 dimensions total. Matching string theory, and the boundary theory was a specific 4-dimensional quantum field theory related to the strong nuclear force. Now, here's what's really wild about this. The correspondence means that a problem that's incredibly hard to solve in one description might be easy in the other. If you're trying to understand what happens inside a black hole, a gravitational question, fiendishly difficult, you can translate it into a question about hot plasma on the boundary, which might be tractable. If you're trying to understand a strongly interacting quantum system where particles are constantly entangling and interacting, and you can't use the usual perturbative tricks, you can translate it into a classical gravity problem in one higher dimension, where the math might be much more manageable. It's like having a dictionary between two completely different languages and discovering that a sentence that's impossibly convoluted in one language becomes simple and clear in the other. And people have actually used this. Physicists studying the quark-gluon plasma. That's the incredibly hot, dense state of matter that existed microseconds after the Big Bang, and that gets recreated briefly in heavy ion collisions at places like the relativistic heavy ion collider at Brookhaven. They've used the ADS/CFT correspondence to calculate properties of this plasma, things like its viscosity, how it flows, and the results matched experimental observations remarkably well. So here you have a tool born from string theory and higher dimensional thinking being used to make predictions about actual experiments, even though the extra dimensions themselves haven't been directly detected. It's this wonderfully indirect kind of usefulness, but the implications go even deeper than practical calculations. The ADS/CFT correspondence touches on something almost philosophical. The idea that the number of dimensions a universe has might not be a fixed, absolute fact. If a 5-dimensional gravitational universe is exactly the same as a 4-dimensional non-gravitational universe, then in what sense does the 5th dimension really exist? Both descriptions are complete. Both are correct. They're not approximations of each other. They're genuinely equivalent. This is sometimes called the holographic principle because it's reminiscent of how a 2-dimensional hologram encodes all the information needed to reconstruct a 3-dimensional image. The idea is that maybe the deepest description of our universe involves fewer dimensions than we think, and the dimension we experience as depth, as volume, as the interior of space. Maybe that's emergent. Maybe it arises from the way information is organized on a lower dimensional boundary. This idea actually connects back to work by Gerard 't Hooft and Leonard Susskind from the early and mid-1990s before Maldacena's paper. They were thinking about black holes and a puzzle called the black hole information paradox. What happens to information that falls into a black hole? Does it get destroyed when the black hole eventually evaporates? That would violate quantum mechanics. 't Hooft and Susskind independently proposed that all the information inside a black hole is somehow encoded on its surface, on the event horizon, like data written on the skin of a bubble. The amount of information a region of space can contain isn't proportional to its volume, as you'd naively expect. It's proportional to its surface area. That's a stunning result. It suggests that the 3-dimensional interior is in some sense a projection, a reconstruction from 2-dimensional data. Maldacena's correspondence gave this vague, suggestive idea a precise mathematical realization. And this thread has led to one of the most active areas of theoretical physics today: the connection between quantum entanglement and the geometry of spacetime. There's a beautiful conjecture, put forward by Mark van Ramsdonk around 2010, that space-time itself might be stitched together by quantum entanglement. If you take two regions of the boundary theory, and they're entangled with each other, that entanglement corresponds to a geometric connection, a bridge, a piece of space-time, between the corresponding regions in the bulk. If you remove the entanglement, the space-time tears apart. Space, in this picture, isn't fundamental. It's woven from quantum information, and the thread connecting two entangled particles, what Einstein dismissively called spooky action at a distance, might literally be a tiny wormhole, a microscopic bridge through a higher dimension. This idea, sometimes written as ER equals EPR, connecting Einstein-Rosen bridges with Einstein-Podolsky-Rosen entanglement, was proposed by Maldacena and Susskind in 2013. It's speculative, it's unproven, but it's one of those ideas that feels like it might be pointing at something very deep. So think about what's happened here. We started this whole journey with Riemann standing in front of his colleagues in Göttingen in 1854, nervously proposing that space might have any number of dimensions and any kind of curvature. And now, 170 years later, his intellectual descendants are seriously investigating the possibility that the dimensions of space aren't fundamental at all, that they emerge from something deeper, something involving quantum information and entanglement. The extra dimensions haven't gone away. They've become richer, stranger, more subtle. And there's another direction where higher dimensional thinking has proven unexpectedly powerful. And it's worth mentioning because it's so different from anything we've talked about so far. It involves condensed matter physics, the study of how electrons behave in solid materials, in metals and insulators and semiconductors. In 2005, Charles Kane and Eugene Mele at the University of Pennsylvania predicted a new kind of material called a topological insulator. These are materials that are insulating in their interior, but conduct electricity perfectly on their surfaces. And the mathematics that describes them, the classification of these exotic states of matter, turns out to involve the same kinds of topological and geometric tools that were developed for understanding higher dimensional spaces and string theory. The connections aren't superficial. The mathematical structures are genuinely the same. Concepts from higher dimensional geometry, things like fiber bundles and Chern classes and topological invariants, turned out to be exactly what was needed to understand how electrons organize themselves in certain crystals. This led to a Nobel Prize in Physics in 2016, awarded to David Thouless, Duncan Haldane, and Michael Kosterlitz for their work on topological phases of matter. It's a beautiful irony when you think about it. The mathematics of extra dimensions, developed partly to describe physics at scales trillions of times smaller than an atom, turned out to be essential for understanding the behavior of electrons in materials you can hold in your hand. The abstract became concrete, the speculative became practical, and it happened not because anyone planned it, but because mathematics has this uncanny ability to show up in places you never expected. There's a famous essay by the physicist Eugene Wigner, written in 1960, called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner marveled at the fact that mathematical structures developed for purely abstract reasons kept turning out to describe the physical world with eerie precision. The history of higher dimensions is maybe the most dramatic illustration of Wigner's point. Riemann didn't develop his geometry to help Einstein. Calabi didn't conjecture about those special manifolds to help string theorists. The mathematics came first, developed for its own sake, and then the physics caught up, sometimes decades later, and found that exactly the right tools were already sitting there, waiting. And this brings us to something that I think is worth holding in your mind as you drift off tonight. A question that doesn't have a clean answer, but that's worth asking anyway. What is a dimension really? We started with something so intuitive: length, width, height, the three directions you can point in. And then we added time, and that was strange but manageable. And then we added 6 or 7 more, curled up so small we can't see them, and that was deeply strange. And then we encountered the holographic principle, which suggests that maybe one of the dimensions we think we see isn't fundamental at all, that it emerges from quantum entanglement on a lower dimensional surface. So the concept of dimension has gone from being the most basic, obvious thing about reality, how many directions can you move in, to being something fluid, contextual, maybe even emergent. Something that isn't baked into the fabric of reality from the start, but that arises, that appears, depending on how you look, depending on what questions you're asking, depending on what scale you're probing. And honestly, that might be the deepest thing we've touched on all night. Think about it. A dimension used to be a ruler, a yardstick, something a carpenter would understand. You measure left-right, you measure forward-back, you measure up-down, and you're done. 3 numbers, 3 dimensions, end of story. That's how Euclid would have thought about it, more or less. That's how Newton thought about it. That's how anyone with common sense thinks about it when they're arranging furniture or parking a car. Dimensions are directions. They're the axes of the world. But then Riemann came along in 1854 and said, well, actually, a dimension is just an independent parameter. It's any quantity you need to specify to pin down a state, a location, a configuration. And once you define it that way, 3 is just a starting point. You could have 4. You could have 40. You could have infinitely many. Riemann didn't say the extra dimensions were real, physical, spatial. He just said the mathematics works, and it works beautifully, and maybe we should pay attention to that. And then Minkowski took that idea and made the 4th dimension not just mathematical, but physical. Time became a dimension, not a metaphorical dimension, not a poetic dimension, an actual geometric dimension, woven into the same fabric as space. After 1908, physicists stopped thinking of space and time as separate things and started thinking of space-time as a single, 4-dimensional object. And that wasn't just a convenient trick. It was necessary. Without it, you couldn't write down the equations of special relativity in a clean way. The physics demanded the geometry. And then Einstein went further. He took Riemann's curved geometry. Remember, Riemann had shown that spaces could be curved, that the rules of Euclid didn't have to hold everywhere, and he applied that to 4-dimensional spacetime itself. Gravity became curvature. Mass told spacetime how to bend, and spacetime told mass how to move. And suddenly a dimension wasn't just a direction or a parameter. It was something dynamic, something that could stretch and warp and ripple, something that could be born in a big bang and expand for billions of years. The dimensions themselves became part of the story, not just the stage the story was set on. And then Kaluza-Klein added a 5th dimension, curled up into a tiny circle, and showed that electromagnetism, a completely different force, just fell out of the geometry. And then string theory said, actually, you need 10 dimensions, or 11 if you're doing M theory, and 6 or 7 of them are compactified into these intricate little shapes called Calabi-Yau manifolds, shapes so small that no experiment we've ever built can see them directly. And the properties of those shapes, their topology, their geometry, how many holes they have, and how those holes are threaded, Those properties determine the kinds of particles we see, the forces we feel, the constants of nature that make our universe what it is. So now a dimension isn't just a direction, and it isn't just a parameter, and it isn't just something that can curve. It's something that can hide, something that can be there, physically real, affecting everything, and yet completely invisible because it's wrapped up at a scale of 10 to the minus 35 meters. And then, and this is where tonight's journey has really been heading, I think, the holographic principle came along and suggested something even stranger. That maybe one of the dimensions we think we see, one of the large, obvious, macroscopic dimensions, isn't fundamental either. That maybe the information content of a region of space scales not with its volume, not with 3 dimensions, but with its surface area, with 2 dimensions. That maybe, in some deep sense, the 3-dimensional world you experience is a projection, a hologram, encoded on a 2-dimensional boundary. Maldaceni's ADS/CFT correspondence made this precise. A theory with gravity in 5 dimensions is exactly equivalent to a theory without gravity in 4 dimensions. Not approximately equivalent. Exactly. Every calculation you can do in one, you can do in the other. And you get the same answer. So which is real? The 5-dimensional world with gravity, or the 4-dimensional boundary without it? And the answer that most physicists have settled on, uncomfortably, is both, or neither. Or the question doesn't quite make sense the way we're asking it. The 2 descriptions are dual to each other. They're different languages for the same underlying reality. And in one language, there are more dimensions than in the other. Which means the number of dimensions isn't a fixed property of the universe. It's a property of the description. Let that sink in for a moment. The number of dimensions might not be a fact about reality. It might be a fact about how you choose to talk about reality. And then, Van Ramsdonk's insight that spacetime itself might emerge from quantum entanglement pushes this even further. If the geometry of space, the very thing that gives rise to our sense of dimensionality, is built from the pattern of quantum correlations between particles on a boundary, then dimensions aren't fundamental building blocks at all. They're emergent. They're what you get when a vast number of quantum degrees of freedom are entangled in the right way. Change the entanglement, and you change the geometry. Destroy the entanglement, and the space itself tears apart, pinches off, ceases to exist in any meaningful sense. This is a genuinely radical idea. For thousands of years, space was the arena. It was the thing everything else happened inside of. It was the given, the absolute. Newton called it the sensorium of God, the medium through which the divine perceives and acts. Even Einstein, who showed that space could curve and stretch, still treated it as a real thing, a physical entity with its own dynamics. But now, in the early 21st century, some of the deepest thinkers in theoretical physics are suggesting that space itself and its dimensionality might be secondary, derivative. That the truly fundamental description of reality might not involve space or dimensions at all, but might instead be written in a purely quantum mechanical language, a language of information and entanglement and operators acting on Hilbert spaces, from which something that looks like space, something that looks like 3 dimensions or 4 dimensions or 10 dimensions, gradually crystallizes the way a snowflake crystallizes from water vapor. Not because the dimensions were there all along, hiding, but because they emerge from something deeper. Now, I want to be honest with you. This is the frontier. This is where the solid ground of established physics gives way to the marshland of active research, where ideas are being tested and debated and revised in real time. Nobody has a complete theory of emergent spacetime. Nobody can yet derive, from first principles, why we experience 3 large spatial dimensions and 1 time dimension. Nobody can prove that the holographic principle applies to our actual universe, which is expanding and has a positive cosmological constant, rather than the idealized anti-de Sitter spaces where Maldaceno's correspondence is best understood. These are open questions, hard questions, the kind of questions that might take another generation, or several, to answer. But here's what I find so beautiful about all of this, and I hope you do too. Even as your eyes are getting heavy and the details are starting to blur together in that pleasant, sleepy way. The journey we've taken tonight, from Euclid's axioms to Riemann's manifolds, from flatland to Minkowski's spacetime, from Kaluza's 5th dimension to string theory's 10, from the holographic principle to emergent spacetime. That journey is one of the great intellectual adventures in human history. And it's not finished. It's still unfolding. And the thing that ties it all together, the thread that runs through every chapter of this story, is a simple willingness to ask, what if there's more than what we can see? What if the world has structure that's hidden from us, not because it's mystical or supernatural, but because our senses evolved to navigate a very specific environment at a very specific scale, and that environment only reveals a fraction of what's really going on? Every major leap forward in this story came from someone who was willing to take that question seriously. Riemann was willing to imagine geometries with any number of dimensions. Minkowski was willing to treat time as a dimension on equal footing with space. Kaluza was willing to add a dimension nobody asked for and see what happened. The string theorists were willing to follow the mathematics wherever it led, even when it led to 10 dimensions and Calabi-Yau manifolds and a landscape of 10 to the 500 possible universes. And Maldacena was willing to propose that 2 theories in different numbers of dimensions could be secretly the same theory. Each time, the instinct was the same. Trust the mathematics. Follow the logic. Don't flinch when the answer is strange. And then check, rigorously, honestly, relentlessly, whether the strange answer makes predictions that match reality. Sometimes it does. General relativity's predictions have been confirmed to extraordinary precision. The holographic calculation of quark-gluon plasma viscosity matched the experiments at Brookhaven. Topological insulators, predicted using higher dimensional mathematical frameworks, are real materials sitting in real laboratories. Sometimes the confirmation is still pending. String theory's extra dimensions haven't been directly detected, and maybe they never will be, at least not with the technology we can currently imagine. And that's okay. That's how science works. You follow the thread as far as you can, you test what you can test, and you hold the rest lightly, as possibility, as conjecture, as a beautiful maybe. And you know what? Maybe that's a good way to think about dimensions themselves. Hold them lightly. They're real enough when you're measuring a room or navigating a city. They're real in a different way when you're calculating the curvature of space-time around a black hole. They're real in yet another way when you're compactifying a Calabi-Yau manifold to recover the particle spectrum of the standard model. And they might not be real at all in the deepest sense if space-time turns out to be emergent. If the truly fundamental description of reality is something dimensionless, something pre-geometric, something we don't yet have the language to fully describe. The concept of dimension has been our companion all night. It started as the simplest thing in the world, just counting directions, and it ended as one of the most profound and contested ideas in all of physics. And the fact that something so basic, so seemingly obvious, can contain that much depth, that many surprises, that much mystery. Well, that's why people spend their lives thinking about these things. So as you settle in, as the thoughts slow down and the edges of the ideas start to soften and blend, just let this wash over you. You live in a universe that is far stranger and far more beautiful than it looks. The 3 dimensions you move through every day might be the whole story, or they might be a thin slice of something much larger, or they might be a holographic projection of something with fewer dimensions, or they might emerge from something that has no dimensions at all. We don't know yet, and that not knowing isn't a failure. It's an invitation. It's the universe saying, there's more here. Keep looking, keep asking, keep wondering. And for tonight, that wondering can be gentle. It can be the quiet kind, the kind that doesn't demand answers, the kind that just sits with the mystery and lets it be beautiful, the kind that lets you close your eyes and imagine, just for a moment, what it might be like to step outside the 3 dimensions you know, to see the world from a vantage point that doesn't exist in any direction you can point to glimpse the shape of something vast and intricate and hidden, something that Riemann intuited, and Einstein curved, and Witten unified, and Maldacena reflected. Something that might be the deepest structure of reality, or might be the deepest structure of mathematics, or might, in the end, be both. You don't need to hold on to any of it. Let it go. Let the dimensions fold up, small and quiet, like a thought you'll half remember in the morning. The universe will still be here, strange and deep and full of hidden directions, whenever you're ready to wonder about it again. For now, just rest.